Picture this. Right now, at this very moment, something is changing beneath the waves. Something vast. Something irreversible. You can't see it from the shore, can't feel it in the cool spray of ocean air, but it's there. A transformation so profound that scientists have only recently begun to grasp its full implications. The ocean, that ancient cradle of all life on Earth, is undergoing a metamorphosis. And here's the unsettling part. We're the ones who triggered it. Climate change isn't just melting ice caps or fueling hurricanes. It's rewriting the rules of survival in the deep blue. The water is warming, acidifying, losing oxygen. Dead zones are spreading like shadows across the seafloor. The old order of predator and prey, honed over millions of years, is collapsing. But nature doesn't leave vacancies unfilled. Let me ask you something that might keep you up at night. What happens when you remove the top predators from an ecosystem and simultaneously subject everything else to extreme evolutionary pressure? The answer isn't extinction, not entirely. It's adaptation. Rapid, desperate, sometimes grotesque adaptation. Scientists studying today's oceans are documenting changes that would normally take hundreds of thousands of years, compressed into mere decades. Fish populations are shifting their ranges by hundreds of miles. Species are breeding at different times, growing to different sizes, developing new behaviors. This isn't gradual evolution from your textbook. This is evolution in fast-forward, driven by survival instinct and environmental chaos. And when evolution accelerates, strange things emerge from the depths. The numbers tell a story more disturbing than any science fiction. Since the Industrial Revolution, our oceans have absorbed over 500 billion tons of carbon dioxide. Imagine dumping more than 500 billion Volkswagen Beetles into the sea. This absorption has increased ocean acidity by 30 to 40%, a rate 10 times faster than anything in the last 55 million years. The ocean's pH has dropped from 8.2 to 8.1, and while that decimal point might seem trivial, it represents a fundamental shift in ocean chemistry. Shells become brittle, coral skeletons weaken, entire food webs begin to unravel. But here's where it gets truly eerie. We've crossed a threshold. In 2025, scientists confirmed that ocean acidification has breached one of the 9 planetary boundaries essential for life on Earth. We're not approaching a tipping point anymore. We've passed it. Now imagine you're a deep-sea researcher, dropping sensors into water that seems unchanged on the surface but is chemically alien beneath. Your instruments detect something unexpected. Massive oxygen-depleted zones spreading like underwater deserts, temperatures rising in currents that have flowed unchanged for millennia, acidification reaching depths of 200 meters and beyond. The Arctic is acidifying faster than anywhere else on the planet. Tropical reefs are dissolving slowly, their calcium carbonate structures unable to form properly in the altered water chemistry. These aren't isolated incidents but symptoms of a systemic transformation. The ocean is becoming hostile to the life forms that have dominated it for eons. But hostility doesn't mean emptiness. It means opportunity for whatever can adapt. This is where our story takes its most unsettling turn. When you push an ecosystem to its breaking point, when you remove stability and introduce chaos, you create what evolutionary biologists call a selective pressure cooker. Traditional apex predators, the great sharks, the tuna, the billfish, have been decimated by overfishing and habitat loss. Their populations have crashed by 70 to 90% in many regions. The niches they occupied are suddenly vacant. Meanwhile, the remaining species are bombarded by new challenges. Warmer water, lower oxygen, altered chemistry, shifting food sources. Some will die out, but others will adapt. And adaptation, when it happens this fast, this desperately, can produce forms that seem almost alien in their strangeness. Recent sonar readings from deep ocean surveys have detected unusual activity patterns in regions previously mapped as biological deserts. Fishing crews report encounters with species behaving in ways their experience doesn't explain. Coordinated movements where chaos should reign, predatory behavior from traditionally passive species, creatures appearing in waters too warm or too shallow for their kind. These aren't myths or fishermen's tales but documented observations that don't fit our models of marine behavior. Something is shifting in the behavioral ecology of ocean life, responses to stress that we're only beginning to catalog. When animals face existential pressure, when their world becomes unrecognizable, they don't simply accept fate. They find new strategies, new alliances, new ways to hunt and feed and survive. Consider the implications for just a moment. Evolution doesn't pause to consult our expectations or comfort level. It experiments ruthlessly, trying every possible variation, keeping whatever works in the moment. In stable environments, this process unfolds slowly, refinements accumulating over geological timescales. But in chaos, in crisis, evolution accelerates. Traits that would normally be weeded out as too strange, too specialized, too extreme suddenly become advantages. The bizarre becomes viable. The monstrous becomes competitive. We're creating conditions the ocean hasn't experienced in millions of years, not since the great extinction events that reshaped life on Earth. And from those ancient catastrophes, new forms emerged. Stranger forms. Predators unlike anything that came before. So here we stand, witnesses to the opening act of something unprecedented in human history. Evolution happening fast enough to observe within a single lifetime. The ocean is changing. The chemistry is wrong. The temperatures are rising. The oxygen is fading. The old rulers are falling. And in the resulting power vacuum, in the ecological chaos, something new is beginning to stir. We don't know yet what forms will emerge from this crucible, what adaptations will prove successful, what body plans will dominate the oceans of 500 years from now. But make no mistake, they're coming. Evolution is blind but relentless. The ocean will have its predators. The only question is, what will they look like? And that's where our journey into the future truly begins. Let's talk about something that should unsettle you on a fundamental level. There's a creature living in our oceans right now whose brain evolved completely independently from ours, separated by some 750 million years of evolutionary divergence, yet somehow arrived at intelligence through an entirely different pathway. The octopus, not a fish, not even remotely related to us vertebrates, but a mollusk, more closely related to snails and clams than to anything with a backbone. Yet when researchers study octopus cognition, they find problem-solving abilities that rival some mammals, memory systems that boggle neuroscientists, and a distributed nervous system so alien that we barely understand how it functions. 2/3 of an octopus's neurons aren't even in its brain. They're in its arms, which can make decisions independently, communicating with each other without consulting central command. This isn't just unusual. This is biological science fiction made real. Now here's where it gets truly fascinating and more than a little disturbing. Recent research has discovered that octopuses possess 42 novel microRNA families in their neural tissue, the third largest expansion of microRNAs in the entire animal kingdom, and the largest outside of vertebrates. These regulatory genes control how other genes express themselves, essentially fine-tuning brain development and complexity. The same mechanism that allowed vertebrates to develop complex cognition appears to have evolved independently in cephalopods through an entirely separate genetic pathway. Think about what that means. Intelligence isn't a fluke, isn't a single lucky mutation that happened once. It's something evolution can stumble upon through completely different routes, using completely different molecular tools. If it happened twice on Earth, using different blueprints, what could it produce under extreme pressure in a rapidly changing ocean? Let me paint you a picture of what we're dealing with right now, today, before we even talk about the future. Octopuses can unscrew jar lids from the inside of sealed containers. They can navigate complex mazes, remember solutions, and apply that knowledge weeks later. They recognize individual humans, form preferences, and yes, they hold grudges. There are documented cases of octopuses in research facilities who learned to short-circuit bright lights they didn't like by squirting jets of water at the bulbs. Others have escaped from their tanks, traveled across laboratory floors, entered other tanks to hunt fish, then returned to their own enclosures before morning. They can change not just their color but their texture, their apparent size, their entire body shape in milliseconds. They are masters of deception, mimicry, and what can only be called creative problem-solving. And they do all this with a brain built on principles fundamentally different from ours. But here's the evolutionary paradox that should make your skin crawl. Octopuses are short-lived loners. Most species live only 1 to 2 years. They don't form social groups, don't have parents to teach them, don't accumulate cultural knowledge across generations. Every octopus that's born has to figure out the world from scratch, armed only with instinct and an absurdly powerful brain. The two dominant theories of intelligence evolution, the ecological intelligence hypothesis and the social intelligence hypothesis, don't fully explain cephalopods. Current research suggests that when octopuses lost their protective shells millions of years ago, they faced a sudden explosion of predation pressure. Their response? Get smart or get eaten. They chose smart. Intelligence emerged not from leisure or social complexity but from desperate, immediate survival pressure. They evolved genius-level cognition in a biological eye blink because the alternative was extinction. Now project this forward. Imagine what happens when you take a creature already predisposed to rapid cognitive evolution and subject it to the most intense selective pressures the ocean has experienced in millions of years. Warming waters, acidification, collapsing food webs, dying coral reefs, traditional predators vanishing. The octopus's short generation time, that 1 to 2 year lifespan, suddenly becomes a massive evolutionary advantage. Where sharks might take decades to show adaptive changes, octopuses could evolve noticeably different behaviors and capabilities in mere human generations. 50 years could see 25 to 50 octopus generations, each one selecting for traits that work in the new ocean. Fast reproduction plus high intelligence plus environmental chaos equals an evolutionary pressure cooker operating at maximum heat. Consider what adaptations might emerge under these conditions. Octopuses are already asocial, but what if extreme food scarcity drives them toward cooperation? Pack-hunting octopuses, coordinating attacks with their distributed intelligence, each arm potentially acting as an independent hunter while the central brain orchestrates strategy. Recent discoveries show that octopus brains use activity patterns similar to the mammalian hippocampus, the region responsible for learning and memory. What happens when memory becomes crucial for survival? Longer-lived individuals who can remember more, who can pass on learned behaviors not genetically but through demonstration. We're talking about creatures that might develop protoculture, cumulative knowledge, teaching behaviors, all built on neural architecture completely unlike anything we've seen achieve this before. The vertical lobe of their brain already specializes in learning visual characteristics. Imagine that capability expanded, refined, weaponized by selection pressure. And here's where the horror really sets in. These aren't theoretical, far-future possibilities. Researchers are already documenting unusual octopus behaviors in warming oceans. Day octopuses forming temporary aggregations in areas where they've traditionally been solitary. Species appearing in waters far outside their historical ranges. Aggressive territorial behavior in populations previously non-confrontational. These might be early warning signs of something larger, behavioral plasticity that could become genetic change within a few dozen generations. We're not talking about new species in 500 years. We're talking about the groundwork being laid right now, adaptations emerging in real time that could compound into something genuinely alien. An octopus that lives longer, that hunts cooperatively, that learns from others and remembers across seasons, wouldn't just be a different species. It would be a different category of marine intelligence entirely. So when we ask what the apex predators of tomorrow's ocean might look like, the cephalopod scenario isn't just plausible, it might be inevitable. They have the intelligence, the adaptability, the evolutionary speed, and crucially, they're already starting from a position of startling cognitive sophistication. A future ocean dominated by octopus lineage predators wouldn't feature simple animals filling empty niches. It would feature intelligent, problem-solving, potentially cooperative hunters whose distributed nervous systems make them nearly impossible to kill without destroying them completely, whose camouflage abilities make them functionally invisible, whose flexibility allows them to enter any crevice or crack. Picture coordinated hunting pods of octopuses that can communicate through color changes and touch, that remember productive hunting grounds and successful strategies, that can manipulate their environment with 8 prehensile arms tipped with hundreds of independently controlled suckers. Picture them operating with collective intelligence, individual genius multiplied by group coordination. The ocean has never seen anything like it. And if we're honest, the thought of what they might become should absolutely terrify us. There's something profoundly unsettling about the deep ocean, isn't there? That crushing darkness beyond the reach of sunlight, where pressure would collapse your body like a tin can, where the temperature hovers just above freezing, where bizarre creatures drift through an eternal night that humanity only glimpsed for the first time a few decades ago. We've explored less than 5% of the ocean floor, less than the surface of Mars. The deep sea remains Earth's last true frontier, home to life forms so strange they seem lifted from nightmares or science fiction. Translucent bodies, elongated jaws bristling with needle teeth, eyes the size of dinner plates, bioluminescent lures dangling from grotesque appendages. These creatures evolved in stable isolation for millions of years, perfectly adapted to an environment so extreme it might as well be another planet. But that stability is ending. And when you destabilize the abyss, when you force evolution's hand in the deep places of the world, the results might be more terrifying than anything currently lurking there. Let's establish something crucial. The deep sea isn't empty. Far from it. Below 200 meters, beyond where sunlight penetrates, an entire biosphere thrives in permanent darkness. Giant amphipods the size of dinner plates scavenge the ocean floor. Vampire squid drift through the water column with their arms turned inside out, looking like something summoned rather than evolved. Gulper eels open jaws wider than their bodies to swallow prey whole. Viperfish bare fangs so long they can't close their mouths. These aren't decorative oddities. They're apex predators of their realm, perfectly engineered killing machines adapted to an environment where food is scarce. Encounters are rare, and every calorie counts. They evolved under selective pressure just as intense as anything in the sunlit zones, just different. Low metabolism, efficient movement, opportunistic feeding, sensory systems tuned to detect the slightest movement, the faintest chemical signature, the dimmest bioluminescent flash in absolute darkness. Now here's where our story takes its darkest turn. Ocean acidification and warming aren't surface phenomena. They're penetrating deep. Recent research has revealed that acidification has already reached depths of 200 meters and beyond, far faster than models predicted. The Southern Ocean, where deep water rises toward the surface, shows pteropod shells already dissolving, their delicate aragonite structures unable to form properly in the altered chemistry. Deep-sea coral reefs off Southern California are experiencing pH levels lower than any previously recorded on living reefs. A glimpse of what most deep reefs will face by century's end. And the corals aren't just struggling to grow. Their skeletons are becoming porous, brittle, fracturing under their own weight in a condition researchers have grimly labeled coral porosis. The osteoporosis of the sea, reaching into the abyss itself. The deep ocean is becoming hostile to the life that built its ecosystems. But hostility creates opportunity. When you dissolve the shells of snails and crush the skeletons of corals, when you make calcium carbonate structures impossible to maintain, you don't eliminate life, you eliminate specific strategies for survival. Shell builders die. Heavily calcified organisms crumble. But creatures that never relied on calcium structures? Creatures with chitinous exoskeletons, with cartilaginous skeletons, with soft bodies and flexible forms? They face a suddenly emptier ocean with fewer competitors and abundant dying prey. Studies have already documented this. Crustaceans like crabs and lobsters often grow stronger shells under higher acidity, their chitin-based structures unaffected or even enhanced by conditions that devastate mollusks and corals. The very chemistry that kills one group empowers another. And in the deep sea, where generation times can be surprisingly short for invertebrates and where environmental pressure is now extreme, evolution can work with startling speed. Imagine what rises from the deep as these changes accelerate. Giant isopods, those oversized pill bugs already haunting the ocean floor, freed from competition with calcifying species. Amphipods expanding into new niches, their scavenging lifestyle perfect for an ocean where mass die-offs create fields of carrion. Species that currently hunker in the deepest trenches, evolve to survive in the most extreme conditions Earth offers, suddenly finding shallower waters accessible as oxygen levels drop and temperature zones shift. Deep-sea organisms are already adapted to low oxygen. It's normal for them. Low pH? Many deep-sea environments naturally have lower pH than surface waters. These creatures evolved in conditions that would kill surface species. What happens when those conditions spread upward? creating highways for abyssal invasion. What happens when the monsters of the deep find themselves suddenly competitive in waters that used to be too rich, too oxygenated, too bright for their kind? The biology gets genuinely disturbing when you consider specific adaptations. Bioluminescence, for instance, incredibly common in the deep sea, used for hunting, communication, defense, and camouflage. In the dark abyss, light is a weapon. Now picture those same organisms migrating into shallower but cloudier waters, into areas where algal blooms and dead zones have reduced visibility. Bioluminescent predators that evolve to hunt in pitch darkness would have an unprecedented advantage in merely murky conditions, their prey unable to see the attack coming until paralyzed by the flash. Or consider jaw structure. Deep-sea predators often have disproportionately huge mouths because in the abyss, you can't afford to be picky about meal size. Every encounter might be your only meal for weeks. Those adaptations become overwhelming advantages in food-scarce shallow waters depleted by climate change and overfishing. A predator that can swallow prey its own size doesn't worry about hunting efficiently. It worries about swallowing everything it encounters. And size? Oh, this is where it gets truly unsettling. Deep-sea gigantism is a well-documented phenomenon. Colossal squid with eyes the size of basketballs. Japanese spider crabs with leg spans of 4 meters. Giant tube worms as thick as your arm. The prevailing theory suggests gigantism evolves in response to cold temperatures, high pressure, and food scarcity. Larger bodies are more energy efficient under those conditions. But if deep-sea giants migrate upward as conditions change, they enter waters with more abundant food, higher temperatures that speed metabolism, and less pressure allowing for even more efficient movement. What happens to a species already predisposed to gigantism when you remove the constraints that limited their size? Recent observations have noted deep-sea species appearing in waters far shallower than their historical ranges, testing boundaries, exploring new territories. These aren't isolated incidents but potential harbingers of wholesale range shifts. The creatures of nightmare, ascending. So when we envision the apex predators of 500 years hence, the deep-sea invasion scenario offers perhaps the most alien possibility. Not intelligence like cephalopods, not familiar forms adapting, but genuinely otherworldly body plans conquering new territory. Picture translucent predators with bioluminescent lures hunting in perpetual twilight zones that extend ever closer to the surface. Giant isopods becoming the new bottom feeders, their armored bodies impervious to predation, their scavenging efficiency unmatched. Massive amphipods developing active hunting strategies instead of passive scavenging, their numbers exploding in the absence of calcifying competitors. Deep-sea fish with distensible stomachs and enormous jaws becoming the new apex predators of midwater zones, their metabolic efficiency allowing them to outcompete everything else when food grows scarce. And perhaps most disturbing, entirely unknown species, residents of the 95% of ocean we haven't explored, emerging from trenches and abyssal plains we've never surveyed, adapted to conditions that are now spreading throughout the entire water column. We won't see them coming because we never knew they existed. The deep is rising, and we have no idea what comes with it. Here's an uncomfortable truth about evolution. Prey don't have the luxury of fighting fair. When you're hunted relentlessly, when your species teeters on the edge of extinction, when predators decimate your population generation after generation, you adapt or you vanish. And the adaptations that emerge from desperation can be far more radical than anything produced by comfortable evolutionary success. We tend to think of prey animals as victims, passive participants in the drama of predation. But evolution doesn't care about our narratives. It only cares what survives. And sometimes what survives is the prey that stops being prey. Sometimes the hunted become hunters. Sometimes the meek don't just inherit the earth, they devour it. This scenario might be the most disturbing of all because it represents a fundamental inversion of everything we understand about ocean food webs, driven by the single most destructive force in marine ecosystems, industrial fishing. Let's establish the baseline carnage. Since 1950, humanity has removed more than 90% of large predatory fish from the world's oceans. Bluefin tuna, once so abundant they slowed ships passing through their schools, now exist in numbers so reduced that each individual fish can sell for hundreds of thousands of dollars. Sharks, which have ruled the seas for 400 million years, have declined by 70 to 90% across most species. Swordfish, marlin, groupers, all decimated. We haven't just fished these species. We've systematically eliminated the apex predators from ecosystem after ecosystem, creating vacant ecological niches on a scale unprecedented in natural history. Nature abhors a vacuum, but it especially abhors a vacuum at the top of the food chain. When apex predators vanish, the entire structure of an ecosystem reorganizes. Mid-level predators explode in number. Prey species populations boom, then crash as they exhaust their food sources. And in the chaos, in the ecological collapse, something unexpected sometimes emerges. Consider what we're already seeing in overfished waters worldwide. Jellyfish blooms of apocalyptic proportions, clouds of pulsing gelatinous bodies so dense they clog intake pipes and overwhelm beaches. These are opportunistic feeders, and in the absence of fish predators, their populations have exploded. Some jellyfish species have evolved increasingly sophisticated hunting strategies, active pursuit, coordinated movements, even what appears to be learning behavior. Or look at sea urchins, herbivores that typically exist in balance with predators like sea otters and certain fish species. When those predators disappear, urchin populations explode, creating urchin barrens, underwater wastelands where every plant has been consumed, leaving only rock and spines. But here's the twist. Researchers have documented urchins in depleted ecosystems beginning to exhibit carnivorous behavior, actively hunting slow-moving invertebrates when plant matter becomes scarce. Herbivores, developing a taste for flesh out of sheer necessity. Now project this forward under accelerating pressure. Ocean acidification favors creatures without calcium-based shells, including many species we've traditionally classified as prey. Warming waters stress traditional predators while opening new territories for species adapted to variable conditions. Dead zones expand, creating refuges where only the most oxygen-efficient species can survive. Overfishing continues, relentlessly targeting anything commercially valuable, anything large enough to be worth catching. The result? An ocean increasingly dominated not by apex predators but by adaptable, fast-reproducing species that historically occupied lower trophic levels. And when you give opportunistic species access to abundant resources, dead and dying organisms from ecosystem collapse, vacant ecological niches, reduced predation pressure, evolution can work with shocking speed. We're not talking about herbivores slowly evolving into carnivores over millions of years. We're talking about behavioral plasticity becoming genetic change within decades. The mechanisms are already in place. Many prey fish species exhibit schooling behavior so sophisticated it borders on collective intelligence. Sardines, herring, anchovies, they form schools of millions, moving with fluid coordination that allows the group to act as a single superorganism. These schools already engage in defensive behaviors that can be startlingly aggressive. Mobbing predators, surrounding and confusing threats, even ramming attacks when sufficiently provoked. What happens when you remove their predators but maintain intense competition for diminishing food resources? What happens when the selective pressure favors not just defensive coordination but offensive hunting? Imagine schools of small fish developing coordinated hunting strategies, surrounding prey, using their numbers not just for defense but for attack. Individual fish are weak, but a coordinated school of 10,000 individuals acting with collective purpose becomes something entirely different. A living net, a mobile trap, a predator collective. And then there's venom, one of evolution's favorite solutions to the predator problem. Venomous fish already exist throughout the ocean. Stonefish, lionfish, stingrays, countless others. But most venomous marine species use their toxins defensively, as a last resort against predators. Under extreme pressure, defensive venom can rapidly evolve into offensive hunting adaptation. We've seen this evolutionary path in terrestrial snakes, where venom evolved from defensive secretions into sophisticated hunting tools. The same pathway exists in marine environments, just waiting for the right selective pressure. Picture traditional prey fish, perhaps sardines or herring, developing venomous spines not just on their fins but integrated throughout their bodies. A school of such fish becomes not just difficult to eat but actively dangerous to approach. And once you have venom, once you have the chemical toolkit for paralyzing other organisms, the transition from defense to predation is almost inevitable. Why wait for food when you can immobilize it? Perhaps most unsettling is the armor scenario. Sea urchins, sea stars, and various crustaceans already demonstrate that heavy armor can coexist with surprising mobility and even aggression when conditions favor it. Ocean acidification might dissolve calcium shells, but it doesn't affect chitin-based exoskeletons, the material that makes up crustacean shells. In fact, some research suggests that crabs and lobsters may actually benefit from higher acidity, growing stronger shells while their calcifying competitors weaken and die. Imagine selective pressure favoring heavily armored prey species in an ocean where traditional predators are vanishing. Creatures that can't be eaten, don't need to hide, and suddenly face abundant food sources as calcifying species die off around them. These armored survivors might develop increasingly aggressive feeding strategies, transitioning from scavenging to active predation. Why not? They're nearly invincible to attack, energy efficient in low-oxygen waters, and surrounded by weakened prey. The ecological logic is inescapable. So when we envision the ocean 500 years hence, the revenge of the hunted scenario paints perhaps the most alien seascape of all. Not intelligent predators like octopuses, not invaders from the deep, but a complete inversion of traditional predator-prey relationships. Schools of fish moving with hive-mind coordination, hunting in packs that number in the thousands. Venomous swarms that paralyze anything they encounter. Armored invertebrates that fear nothing and consume everything. Jellyfish blooms developing active hunting strategies, using their numbers and their stings to overwhelm prey that once fed on them. Filter feeders evolving into trap feeders, then into active hunters. The meek inheriting the seas not through gentleness but through sheer adaptive persistence, through being too numerous to eliminate, too flexible to constrain, too opportunistic to starve. We created the conditions for this revolution by removing every large predator we could catch, by acidifying the water until traditional success strategies became death sentences, by warming the ocean until stable ecosystems collapsed into chaos. And from that chaos, from the wreckage of the old order, something new is rising. Something that remembers being prey. Something that decided to stop running. Now we enter the territory that should truly make us uneasy, because this scenario isn't speculative biology or distant future projection. It's happening right now in laboratories and ocean pens and accidentally released populations scattered across the globe. We're talking about genetic modification, selective breeding, aquaculture escapes, and the hubris of thinking we can engineer life without consequences. Humanity has been playing God with marine species for decades, creating organisms optimized for growth, disease resistance, environmental tolerance, and commercial value. We've modified salmon to grow twice as fast, engineered shrimp to survive in polluted water, selectively bred tuna for higher fat content and docility. These creations exist in supposedly controlled environments, behind nets and filters and security protocols. But here's the thing about engineered organisms. They don't stay contained. They escape. They breed with wild populations. They spread traits we never intended into ecosystems we barely understand. And in 500 years, the genetic pollution we've unleashed today could create predators that evolution alone would never produce. Let's start with what's already in the water. AquAdvantage salmon, the first genetically modified animal approved for human consumption, contains genes from Chinook salmon and ocean pout that allow it to produce growth hormones year-round instead of seasonally. The result? A fish that reaches market size in half the time of wild salmon. Theoretically contained, theoretically sterile, theoretically safe. Except that containment fails, sterilization is never 100% effective, and safe is a word that loses meaning when you're dealing with evolution. What happens when these fast-growing salmon escape into rivers, which they have, and breed with wild populations, which they inevitably will? You get hybrid fish carrying growth genes, territorial aggression adapted to crowded pen conditions, and feeding behaviors selected for maximum consumption in minimum time. Wild salmon are already fierce predators during their ocean phase. Now imagine that predatory drive combined with engineered metabolic efficiency and aggressive behavior bred through generations of high-density aquaculture. The result isn't just a bigger salmon. It's a more effective killing machine. But salmon are just the beginning. Consider tilapia, the most widely farmed fish on Earth, bred for dozens of generations to tolerate poor water quality, survive in low oxygen, and eat virtually anything. Tilapia escapes are common, and these fish have established invasive populations on every continent except Antarctica. They outcompete native species, devour ecosystems, and adapt to new environments with terrifying efficiency. Now layer climate change on top of that adaptability. Warming waters open new territories. Acidification kills off calcifying prey that native fish depend on, but tilapia, with their flexible diet, thrive. In 500 years, with continued selective pressure, both artificial and environmental, these generalist survivors could evolve into something far more predatory. We've already selected for environmental tolerance, rapid growth, and aggressive feeding. The transition from omnivore to apex predator is merely a matter of selective pressure and time. And we've provided both in abundance. Then there's the truly nightmare scenario. Organisms we're creating not for food, but for environmental cleanup. Scientists have proposed engineering filter-feeding fish to consume microplastics, bacteria designed to break down oil spills, organisms optimized to absorb heavy metals or neutralize toxins. These bioremediators sound beneficial, even necessary given the pollution we've dumped into the ocean. But think about the selective pressures we're creating. An organism engineered to consume microplastics needs to be efficient at capturing tiny particles from the water column, exactly the same mechanism that plankton-eating predators use. An organism that thrives in polluted, low-oxygen dead zones needs the same physiological adaptations that allow apex predators to survive in marginal habitats. We're selecting for predatory traits while calling it environmental protection. And when these engineered organisms escape containment, not if when they enter ecosystems already destabilized by climate change, overfishing, and pollution. The most adapted organism isn't necessarily the most natural one. It's the one we built to survive in the toxic hellscape we created. Genetic engineering technology is accelerating faster than our ability to predict consequences. CRISPR gene editing allows precise modification of any trait we can identify. Want a fish that grows in warmer water? Edit the temperature tolerance genes. Want disease resistance? Modify the immune system. Want aggressive territorial behavior to prevent escapes? Change the neurological response pathways. Each modification seems reasonable in isolation, but genes don't exist in isolation. They interact in complex networks we barely understand. A gene that increases disease resistance might also affect aggression. A modification for temperature tolerance might alter reproductive timing. These unintended consequences compound when modified organisms breed with wild populations, creating hybrid genotypes that express traits in ways we never predicted, never intended, never imagined. And once those genes enter wild populations, you can't recall them. They're there permanently, spreading through sexual reproduction, selection pressure amplifying whatever traits prove advantageous in the chaotic ocean we're creating. Consider what happens when multiple escaped lineages hybridize. Fast-growing salmon genes mixing with disease-resistant tilapia traits. Pollution-tolerant bioremediators breeding with temperature-adapted aquaculture escapes. Each generation produces new combinations, natural selection testing each one against the harsh realities of the transformed ocean. The survivors aren't necessarily viable by natural standards. They're viable by our new standards, the standards of an acidified, warming, depleted ocean where traditional fitness metrics no longer apply. Some hybrids will be sterile dead ends, evolutionary experiments that fail immediately. But others might combine traits synergistically, creating organisms with capabilities that neither parent species possessed. This isn't how evolution typically works. Natural selection usually proceeds gradually, testing small modifications against stable environments. But we've created the perfect storm. Engineered genetic variation, environmental chaos, collapsed ecosystems with vacant niches, and accelerating selective pressure. Evolution on fast forward, guided by our modifications but no longer under our control. And we haven't even discussed intentional releases. As ecosystems collapse and fisheries fail, there will be increasing pressure to introduce modified organisms directly into the wild. not as accidents but as solutions. Modified corals designed to resist bleaching and acidification. Engineered predators to control invasive species. Genetically enhanced versions of depleted commercial fish to replenish stocks. Each intervention will seem necessary, urgent, potentially successful. And some might work, at least temporarily. But we're essentially playing evolutionary roulette with organisms we've only partially understood, releasing them into ecosystems we understand even less, hoping that our interventions improve rather than exacerbate the situation. History suggests otherwise. Every time we've introduced species to solve ecological problems, rabbits in Australia, cane toads in Queensland, Nile perch in Lake Victoria, the results have been catastrophic. Now imagine doing the same thing with genetically modified organisms specifically engineered to outcompete native species. The potential for disaster isn't hypothetical. It's inevitable. So when we envision the apex predators of 500 years hence, the engineered and escape scenario might produce the most unpredictable and potentially horrifying results. Not natural evolution but human-guided modification that escaped our control and continued evolving in directions we never anticipated. Imagine salmon tilapia hybrids with engineered growth rates and environmental tolerance, spreading through warming rivers and coastal waters, outcompeting and consuming every native species they encounter. Picture bioremediator organisms that evolved from pollution eaters into generalist predators, their engineered efficiency at capturing particles adapted into devastating predation capability. Consider coral reef predators modified for disease resistance that bred with wild populations, creating hybrid lineages that survive the acidified conditions killing their ancestors but express their predatory instincts with enhanced aggression and efficiency. These wouldn't be natural predators shaped by millions of years of coevolution. They'd be Frankenstein organisms, assembled from pieces of different species, optimized for conditions that shouldn't exist, thriving in an ocean we've poisoned and genetically polluted beyond recognition. We created them, we released them, we can't control them. And in 500 years, they might not just dominate the ocean. They might be the only large predators left, the inheritors of an ecosystem we destroyed and inadvertently repopulate with our own creations. The ocean of the future might be filled with monsters, but they'll be monsters we made. So we've explored the scenarios one by one: intelligent cephalopods, abyssal invaders, prey-turned predators, genetically modified escapees. Each one disturbing in its own right, each one plausible given the pressures we're exerting on marine ecosystems. But here's what should truly terrify you. These scenarios won't happen in isolation. They'll happen simultaneously, overlapping and interacting in ways we can barely predict. The ocean of 500 years hence won't be dominated by one type of new predator carefully occupying its evolved niche. It will be a chaotic battlefield where multiple evolutionary experiments collide, compete, cooperate, and hybridize into combinations that make each individual scenario look tame by comparison. This is the convergence event, the perfect storm where every pressure, every adaptation, every desperate survival strategy comes together in an ecosystem so alien we might struggle to recognize it as Earth's ocean at all. Imagine the interactions. Pack-hunting octopuses with enhanced intelligence encountering deep-sea gigantism migrants equipped with bioluminescent hunting strategies. Which adaptation wins? Perhaps neither. Perhaps they coexist, each exploiting different niches in the transformed water column. Or perhaps they hybridize, not genetically, they're too distantly related for that, but ecologically, learning from each other's strategies in real time. Octopuses already demonstrate remarkable observational learning. Could they observe and adopt bioluminescent luring techniques from abyssal predators? Could deep-sea invaders learn coordinated hunting by watching cephalopod packs? We tend to think of evolution as genetic change across generations, but behavioral evolution can happen within a single lifetime when intelligent species encounter novel challenges. The convergence isn't just multiple scenarios playing out side by side. It's multiple scenarios informing and accelerating each other's development in ways that produce genuinely unprecedented outcomes. Now layer genetic pollution on top of natural adaptation. Engineered salmon with accelerated growth genes don't just compete with wild populations. They breed with them, introducing artificial traits into natural genomes that then undergo natural selection in the transformed ocean. A fast-growing hybrid might normally be at a disadvantage, burning through energy reserves too quickly. But in warming, food-scarce waters where metabolic efficiency matters more than caution, that engineered metabolism becomes a devastating advantage. Meanwhile, prey species developing defensive armament and venomous capabilities suddenly face predators they never co-evolved with, intelligent octopuses that can learn to avoid toxic species within a single encounter, or abyssal invaders whose simple nervous systems make them immune to neurotoxins that would paralyze more complex predators. Every adaptation creates counterpressure for counter-adaptation. Every survival strategy spawns an arms race. And in an ocean undergoing rapid chemical, thermal, and ecological transformation, those arms races operate at unprecedented speed. Consider the convergence zones, specific regions where multiple scenarios intersect most dramatically. Oxygen minimum zones, areas of naturally low oxygen in the ocean's mid-depths, are expanding rapidly due to warming and nutrient pollution. These dead zones are lethal to most marine life but habitable for species adapted to low oxygen conditions. Certain deep-sea organisms, some engineered aquaculture escapees, and prey species that evolved oxygen efficiency as an escape strategy from predation. As these zones expand, they become highways for organism migration and mixing, places where species that would never naturally encounter each other suddenly compete for the same limited resources. The result? Accelerated evolution, desperate innovation, and the emergence of hybrid strategies cobbled together from whatever works in the moment. Dead zones might sound lifeless, but in the convergence scenario, they become incubators for the most extreme adaptations, refuges where only the most radically transformed species can survive, and from which new apex predators emerge already optimized for the deteriorating ocean. Temperature stratification adds another layer of complexity. As surface waters warm faster than deep waters, the ocean is developing distinct thermal zones with reduced mixing. This creates isolated evolutionary theaters where different adaptive strategies dominate at different depths, but with crucial interfaces where these zones meet, upwelling regions, thermoclines, boundary layers where warm and cold water interact. These interfaces become evolutionary battlegrounds where warm-adapted and cold-adapted predators clash, where surface specialists encounter deep-sea migrants, where every possible combination of traits gets tested simultaneously. Species that can tolerate both temperature ranges, like some engineered organisms specifically designed for variable conditions, or naturally flexible species like certain cephalopods, gain access to multiple zones, becoming apex predators not through superior strength but through superior range. They can hunt in warm surface waters, retreat to deep cold zones to avoid competition, and exploit resources across the entire water column while specialists remain confined to single thermal layers. And we haven't even addressed the most disturbing implication: emergent complexity. When you have multiple intelligent or semi-intelligent species coexisting in proximity, you don't just get competition, you get social dynamics, territorial structures, possibly even cooperative relationships that wouldn't evolve in isolation. Pack-hunting octopuses might develop symbiotic relationships with certain fish species, using them as scouts or bait in exchange for protection. Prey species with collective intelligence might form defensive alliances across taxa, multiple species schooling together to create superswarms that no individual predator can overcome. Deep-sea organisms with bioluminescent communication might inadvertently or deliberately interfere with the signaling of other species, creating false lures, jamming signals, essentially waging information warfare in the depths. These aren't science fiction scenarios. Every behavior described has been observed in isolation somewhere in nature. The convergence event simply puts them all in the same ocean, under extreme pressure, with selection favoring whatever strategy produces survival regardless of how bizarre or unprecedented it might be. The timeline of convergence is already beginning. Right now, today, these scenarios aren't future projections but emerging realities. Octopus populations are expanding in some regions as traditional predators decline. Deep-sea organisms are appearing in shallower waters, documented by researchers and fishers worldwide. Prey species are exhibiting unusual behaviors, coordinated movements, aggressive responses, dietary shifts. Engineered organisms are escaping, hybridizing, spreading. The transformation isn't scheduled for 500 years from now. It's starting now, this decade, this year. The question isn't whether these changes will happen, but how extreme they'll become as pressures intensify over the coming centuries. Each generation of marine life born into a more hostile ocean represents another iteration of the evolutionary algorithm, another test case for what works in the new normal. And because we're talking about species with generation times measured in months to years rather than decades, 500 years represents not 5 human generations but hundreds or even thousands of marine generations. That's enough time for transformation we would normally only see across millions of years of gradual evolution. So when we ask what the apex predators of 500 years hence will look like, the convergence scenario offers the most comprehensive and frankly most terrifying answer. They'll look like nothing we've seen before. Intelligent cephalopod packs with behavioral complexity approaching cetaceans. Gigantic abyssal organisms adapted to bioluminescent warfare in oxygen-depleted waters. Armored swarms of former prey species hunting cooperatively with venomous efficiency. Genetically modified chimeras combining traits from multiple lineages, optimized for survival in toxic conditions we created. And hybrid strategies that mix and match all of the above, predators that switch tactics based on prey type, environmental conditions, and competitive pressure. The ocean won't have a single apex predator. It will have a shifting, dynamic ecosystem of apex predators constantly competing, constantly adapting, constantly evolving in response to each other and to continuing environmental degradation. It will be beautiful in its complexity, terrifying in its alienness, and ultimately a reflection of the chaos we unleashed. We transformed the ocean. Now the ocean is transforming itself in response. And the creatures emerging from that crucible will rule an alien sea on an Earth that's still our home. The convergence is coming. In some ways, it's already here, and there's no going back to the ocean we once knew.